Welcome to the Problemers channel, season 3, episode 4, the episode which I titled A Complex Approach, because in this episode we will find an alternative expression for a certain finite trigonometric sum using the tactical might of complex numbers. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material presented on this channel is for you to go to the homepage of this channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section, and I will do my best to find a time to answer all of your questions. In order to set up a context for what is about to unfold in this episode, recall that across the following 3 episodes, season 3, episode 3, season 3, episode 4, this is this episode, and the next episode, season 3, episode 5, we're coming face to face with the idea that fixing a given technical problem in, say, mathematics, and trying to generate as many distinct enough solutions for that fixed problem as possible should be an integral part of the fabric of studying and doing mathematics and physics and computer science. As such, our current fixed problem is the task of evaluating the following finite trigonometric sum, where we're asked to find an alternative expression, or because we already know what is going on with this sum from season 3, episode 3, we're looking for a way to compress this here finite trigonometric sum into a product. Even though that is not necessarily required, we can leave an alternative expression for that sum as a difference of certain things, but generally we want to fold this into a product. And that finite sum has the following shape. The values of the trigonometric function of cosine evaluated at apparently n+1 arguments, each of which is a member of an arithmetic progression, a plus k times theta, where a and theta are real numbers. K is, in general, non-negative whole number that varies from 0 to n, 0, 1, 2, 3, 4, 5, and so on. And as such, we want to find a way to find what many people refer to as a closed form formula. As I mentioned before, the more you study mathematics, the more you realize that if you put enough mathematicians in the room, it will be quite challenging to find a definition that all these mathematicians will agree on, or what exactly is a closed form formula. So for now, an alternative expression or a way to compress the sum of n+1 terms of this here function into a certain product. This is a standing fixed problem that we need to solve in as many different ways as possible. My sample demonstration for that task, for showing how this process, this idea, the mental habit of fixing a problem and generating as many distinct enough solutions of that problem, should be the integral part of the fabric of studying and doing mathematics. I suggest I put forward 3 distinct enough solutions, and in season 3, episode 3, we solved that problem, exposing the fact that this here sum can be morphed into a sum that possesses a technical advantageous property known as telescopicity. We can manufacture a sum that is telescopic from this sum and the related sum of the values of the trigonometric function of sine. In this episode, season 3, episode 4, we will solve this problem using quite different machinery altogether. We will use the arithmetic of complex numbers. Those of our viewers who studied mathematics far enough and deep enough are likely familiar with this here formula. It belongs to the Swiss-born mathematician Leonard Euler in 1748, if I'm not mistaken. He published this result in one of his works, and I always recommend that when in doubt, read Euler, get as many books as you can muster for Euler in your native tongue and try to read it. If you don't have it in your native tongue, find a book maybe in English. But it is always a good idea to time well spent reading Euler. And in the next episode, season 3, episode 5, we also solve almost exactly the same problem, but we will use nothing more than the synthetic Euclidean plane geometry. As a fair warning, I will eliminate this constant real number a because it will not really affect the result materially. And we will also roll our sums not from 0 but from 1, and for the reasons that I will explain, watch this episode if you want to deal with synthetic Euclidean plane geometry. And without any further ado, let us solve this here problem. This will be our problem S3M3. The previous episode here deals with the problem S3M2, and in episode season 3, episode 5, we will be dealing with the problem S3M4. So in this episode, S3 episode 4, we will solve the standing problem using the arithmetic might of complex numbers. In order to set things up, here are a few words about the underlying geometry of the complex plane as it pertains to our problem, even though I have to say that some authors of complex analysis courses go out of their way to avoid the geometry of complex numbers for the reasons that I personally do not really understand, because the relationship between the algebra and the geometry of complex numbers in particular is very fruitful and symbiotic. And I think that in general, regardless of the vaguely defined mathematical layer, be it the theory of groups, theory of numbers, theory of graphs, complex analysis, real analysis, I think that the relationship between these two domains, the underlying algebra and the underlying geometry, is always quite fruitful. And the ideas that are, for example, generated in the domain of algebra may sometimes find a quite beautiful and elegant interpretation in the domain of geometry and spawn some further development of geometry. And conversely, certain ideas and mechanisms in geometry may find a beautiful algebraic interpretation and spawn or give impetus to the development of the ideas that seem to be purely algebraic. In any case, when it comes to the set of complex numbers and points of the complex plane, it should be understood that technically we're dealing with two very distinct objects. A number is general, is not a geometric point, and conversely, a geometric point is not a number. These two mathematical objects are quite distinct. But when it comes to the relationship between the elements of the set of complex numbers and the elements of the set of points that form the complex plane, there exists a one-to-one correspondence or a bijection. That is, to every complex number, there corresponds a unique point in the complex plane, and conversely, to every point in the complex plane, there corresponds a unique complex number. That can be seen by, for example, the virtue of the algebraic representation of the complex number as x plus iy, where x and y are two real numbers, and then we correlate the real and the imaginary component of a number to a point that has precisely the coordinates as x and y, and conversely we grab a point in the complex plane that has the coordinates x along the real axis and y along the imaginary axis, and we follow that point or correlate that point to the corresponding complex numbers, and voila, we have our bijection. And in particular, as it pertains to our problem, and it will become evident very quickly why that is, if we take the complex number z that has the modulus of 1, then that number in its exponential form is represented as e, the base of the natural logarithm, raised to the power I theta, where I famously has the property that when it's squared, it produces -1 minus 1. I is also a generator of the group of fourth roots of unity that has the following content: plus minus 1 plus minus I under the operation of multiplication of complex numbers. So this set of complex numbers under the operation of multiplications forms a finite commutative group in this case, and one of the generators of that group is precisely the element to which we refer as I. This is this guy right here, and geometrically we now understand that too. Each and every complex number that has this specific shape, there corresponds a point in the complex plane that sits on the periphery of the origin-centered unit circle shown in blue over here, and conversely, to every point that sits on the periphery of the origin-centered unit circle, there corresponds a unique complex number in that shape. And that is why, again, pedantically, initially, we have to understand the distinction between a number as a standalone mathematical object and a geometric point that is a standalone mathematical object. But the thing is, the more you do complex analysis and the more you deal with complex numbers, you realize that the relationship between complex numbers and the points in the complex plane is so natural, so tight, they're so fused together that very quickly we lose all this distinction altogether, and we throw these terms intermittently. We point at the complex number and say, hey, this is a point, or we point at a point in the complex plane with our finger and say, look, gee, this is a complex number, and so on. But pedantically, initially, especially for the folks who are new to the idea of complex numbers, I showed not the equality, but correlates to, let's say, the symbol over here, equal sign with the tilde on top, correlates to. So technically, numbers are equal. This is the true representation. And correlation, let's say we show this way, but again, very soon you will drop even that and you will just say a point is equal to blah, the number, even though technically and pedantically we're committing a crime when we do that. Now, what is the origin center unit circle? The origin center unit circle is a circle of radius 1 that has its center precisely at the center of the complex coordinate system that is formed by the intersection of two orthogonal axes: the real axis, usually taken to be the horizontal axis, and the imaginary axis, taken to be the vertical axis. These two axes intersect at right angles right here. The point of their intersection marked as O. This is the origin, and consequently the origin-centered unit circle is precisely the circle that has radius 1 and positioned at the origin of the coordinate system that is formed as I explained. Here we take the scale along the imaginary axis and real axis to be one and the same, 1. And now in the next few seconds we will be raising our complex number z that has the modulus of 1 and the argument of theta to a, well, in our case we are rolling our sum with k equal to 0, but in general the interesting case is when k is integral and, let's say, positive. Now the thing is, the algebraic property of a complex number to which we refer as its argument, and we know that the argument of a complex number as a function is not a function that is well defined. It is defined up to an integral multiple of 2 pi. The geometric interpretation of that number theta, real number theta, or the argument of the complex number z, is the angular displacement of the corresponding point that sits in the complex plane on the periphery of the origin center unit circle with respect to the positive branch, This is the negative branch of the real axis. This is the positive branch of the real axis. So the geometric interpretation of the argument of the complex number, this is the real number theta, is the angular displacement of the corresponding point with respect to the positive branch of the real axis. And we also recall that complex numbers offer many wonderful things when it comes to, again, to the connection between the algebra and the geometry. And one of such things is it goes a long way. Maybe at some point I will tell that story of how the he was, I think, a Norwegian land surveyor, Caspar Wessel, how he stumbled upon this absolutely beautiful idea of how to geometrically construct, if you will, complex numbers. So here, the act of the geometric operation of raising a complex number, this here number, to, let's say, in general, in our interesting case, positive integral power, k, corresponds to the rotation of the complex plane about origin, in general, in the direction that depends precisely on the signs, on the way in which the signs across k and theta play out. But let's say for demonstration purposes, both k is positive, theta is positive, as shown over here. Then the geometric interpretation of the algebraic operation of raising our complex number z to a, let's say, positive integral power means the rotation of the corresponding point. Technically, it's the rotation of the plane. So we split one plane into two, keep one in place, rotate the other, slap it on the original one, and see what happens. Well, in this case, what happens is that the point z is rotated about origin in the positive or counterclockwise direction, shown over here with an arrow, by exactly the k multiple of theta. In other words, geometrically, the complex number z raised to the power of k corresponds to, again, a point that sits still on the periphery of the origin-centered unit circle shown over here in blue, which is basically displaced angle-wise from the positive branch of the real axis by the angle k theta, as shown over here. And now I will explain how to work in the complex number that has this particular shape as e, the base of the natural logarithm, raised to the power I times a. Perhaps at the root of all this beautiful stuff and the mighty tactical power of complex numbers, there sits a result that the Swiss-born mathematician Leonhard Euler had the courage to publish back in 1748, if I'm not mistaken. And Euler did it by decomposing the three functions involved in this business into the power series, and then realizing that pattern-wise, if you shuffle things around, precisely this happens. If we take, again, a complex number that has modulus of 1 or displaced from the origin precisely by 1 unit of distance, that means it sits somewhere on the periphery of the origin-centered unit circle, as I explained, then this seemingly exponential function e to the power I theta can be represented as a linear combination of the following functions: the trigonometric function of cosine evaluated at the argument theta plus I scaled by the value of the trigonometric function of sine of theta. You see, this is the result. And later on, there was another mathematician, Abraham de Moivre, who worked with this specific sum, raised it to integral power, and realized that the powers, in this case, the power of the whole object, this guy, or essentially this guy and this guy, can be alternatively represented by precisely the same sum. Amazingly enough, is the power n to which this sum is raised are basically lowered into the arguments of these two functions. In other words, algebraically, if we raise our number that has the modulus of 1 to an integral. K is an integer, and in this case, in our case, the interesting case is when it is a whole positive number, 1, 2, 3, 4, 5, 6, 7, and so on. We can write it down as e to the power I k theta. We simply raise this number, lower k into the product over here, and then this becomes the cosine of k theta plus I times sine of k theta. You see, we raise z to the power of k. We raise this sum. Technically, if you want, guys, okay, this will be in a smaller font. I apologize, but I don't have much room. But you will write it like this. This is the Moivre's formula, raised to the power of k, where k is, again, an integer. In general, it works out in such a way that it can be both negative, positive, and 0, but essentially this is what it is. So from here, we jump over here, this way and this way, you see? And then we have this beautiful result, even though, to some extent, if we take the Euler's result, Euler's formula that represents, that connects the complex number that has the modulus of 1 and connects its trigonometric form with its, exponential form with its trigonometric form, then we can say theta is real. We can shuffle theta any legal way which we want. So we can, for example, take theta to be replaced with k theta. And voila, we have our formula, but it doesn't really matter. What we have now, purely algebraically, is the following result. The complex number z that has a modulus of 1 raised to an integral, positive integral power k, has the following exponential shape. The e, the base of the natural logarithm, raised to the power I k theta. And that, amazingly enough, can be unfolded into a linear combination of two of our favorite trigonometric functions. The value of the trigonometric function of cosine evaluated at the argument k theta. See, this is how from the exponent we jump into the argument here, plus I times the value of the trigonometric function of sine evaluated at the argument k theta. And here's how the constant real number a, remember, in our original sum, we have the cosine of what? Cosine of a plus k theta. So now you can already see, again, put this video on pause, think on your own, what will be the next step if you were doing this problem, solving this problem the way I am solving it. See, k theta, we have our constant real number a. Somehow we have to splice a into this here sum. How do we do it? Well, this is how we do it. First, we go back to the Euler's formula and we unfold this here geometric point. But again, you guys probably noticed that even in the previous segment, I already completely lost any distinction between the notion of a number and a geometric point, and I throw these objects interchangeably. This is exactly what will happen to you because this connection is so natural. So technically we have a point designated here in red with the uppercase A that sits on the periphery of the origin centered unit circle, and it is displaced with respect to the positive branch of the real axis by the angular measure of a radians. This is theta radians, k theta radians. Again, all these measures are expressed in radians, and we know that that point corresponds to a complex number that has the following exponential shape of e, the base of the natural logarithm raised to the power of I times a. We go back to our favorite Euler's formula and we express this exponential form of a complex number, which corresponds to a point, blah, blah, blah. You guys understand what's going on in the following way. Cosine of a plus I times sine of a. This is our first step. And what do you think we will do next? What we do now is we algebraically multiply the complex number that is represented in its exponential form as e raised to the power of ia by the complex number z that is raised to the power of k. And the way in which this multiplication will work out is as follows. Let's say we write a times z raised to the power of k will be here. We express both complex numbers algebraically in their trigonometric form. Here I erased the number. Remember the representation of z to the power of k as this exponent over here. So we write it as follows: e raised to the power I times a times e raised to the power I k theta. This is a, this is z to the power of k raised to the power of k. And now here is the thing again. The reason I showed you guys the previous segment and use the Euler's formula to unfold an exponential form of a complex number into its corresponding trigonometric form, because even here we have an opportunity for a very lightweight improvisation, if you will, or lightweight variation. We have choices, and you should be able to see these choices, and you should be able to carry out or carry through the computational program that goes into either branch of this decision tree, if you will. We can multiply this trigonometric functions by the remember that z to the power of k we represented which way? Cosine of k theta plus I times sine of k theta. And then z to the power of k in its trigonometric form times e raised to the power of a in its trigonometric form will be basically a fight of two linear combinations. This animal times this animal. And if you fight this fight with the arithmetic of the underlying trigonometry, cosine k theta times cosine of a plus cosine of k theta plus I times sine eta, and multiply this, open up this parenthesis, multiplying them through and torturing the underlying trigonometric pairs of products of trigonometric functions of cosine of this and cosine of this, sine of this and sine here and this and that. Using the standard middle school identities, you will come to exactly the same result. As here, I will not do that. You guys should try to carry it out on your own and see that it really works out. Here, I will improvise a little bit and take a computational shortcut afforded by the arithmetic of powers, of product of powers. So here the base is the same, so I have the right to write down the following: I e raised to the power of I times a plus k theta. You see, this is where we collect the exponents, lump them into one plus, but I is a common factor in both cases. Factor it out, and here we go: I times a plus k theta. And what do we do now? Go back to Euler, and we write down the following result. So what do we have? Cosine of a plus k theta plus I times sine of a plus k theta. You see, and we basically manufactured what? Well, with this straightforward string of computations, we manufactured common terms in both of our finite trigonometric sum. The sum of cosines, boom, the sum of sines. What's the next step? That's right, multiply and sum. Now we sum this here animal over k from 0 to n, and we sum this here animal and this here animal from over k from 0 to n over k from 0 to n, and voila, we manufactured our finite trigonometric sum of cosines and a finite trigonometric sum of sines. So if we are diligent students of mathematics, let's write down this in a more civilized form. So by carrying out the multiplication and then summing the results over k that varies from 0 to n, we have this result. And remember, this maneuver is quite popular. We can do many things to our identities that we develop that way. For example, we can differentiate both sides over something, over time, over z, over theta, or whatever, both sides uniformly, or we can integrate, or we can do whatever else other mathematical operation we have in mind, but we can do the summation, and in this case the summation will lead to the following. Let's ink this result. So k varies from 0 to n, a times z raised to the power of k equal to the sum that runs from k between 0 and n of cosines of a plus k theta, plus here a is a constant, I is a constant complex number. We can factor it out, so we'll have I times sum that runs over k that varies from 0 to n of the values of the trigonometric function of sine a plus k theta. You see, in one fell swoop, in one operation, we managed to absorb two trigonometric functions, all courtesy of this beautiful, absolutely beautiful relationship here, the so-called Euler's formula. And we manufactured our sum of cosines, and as a free, if you will, byproduct, we also manufactured the sum of sines. And the arguments in this case are exactly what we have. I will now take a small second to erase this material. Maybe in your mind, we're visual animals. Some people think spatially better than they think algebraically, and conversely, some people think algebraically better in some sense, and I'm not even sure what better means, but better than they think spatially. Anyway, this may help to some of our viewers. Keep this idea in mind. So then finally, what is the geometry of this relationship captured over here? Well, technically we have two complex numbers, if you will. Complex number on the right hand side of the equal sign, and the complex number, now I'll say a few words in the next few seconds, a complex number on the left hand side of the equal sign. Complex numbers correspond to points in the complex plane, yada yada. You already understand the drill. So what are we doing with this sum over here? Let's say forget about the right hand sum, this sum. What is the geometry of this sum? Well, we take our number, we take our point that corresponds to this here number, we multiply each time this the number e to the power I theta by this number, and then we will produce the result. What the multiplication of these two complex numbers, again, remember, corresponds to the rotation of the complex plane. So from these 2 points we manufacture yet another point that has the coordinate which way, well, corresponds to the number a plus theta. So it will sit somewhere here, and then we do the same for all the numbers like this. So all these numbers are also multiplied by this number a. So committing a horrible crime, we cannot multiply points. Don't do that. I'm just saying this as parabolically. So the multiplication of numbers corresponds to multiplication of points. Don't really do that at home when you're alone. But the geometric interpretation of this sum then becomes what? We represent each resultant point in the complex plane. Let's say, for example, here we add another a. For each one, we add another a. So this is the point that corresponds to the number e to the power I a plus k theta, right? This is the number. And we want to sum all these guys. So another thing that we can also do is introduce vectors into all these things. So the terminal point of this vector will be this point. The point of origin will be the origin. So what are we doing with this? We're summing all these vectors using the vector summation, and the result, and we'll have a bunch of these vectors. And the way they will interact with each other and their total sum, the way it plays out, we will find an algebraic expression for that. But before we move on to the specific symbolic shuffling, a few words about the situation that is captured over here in this formula. I will take a short break right now. I will rewrite this formula better. I will erase this material. put this video on pause, think about it, copy it, do what you think you need to do. But in the next segment, I will erase this material and I will discuss precisely this situation over here, because it will be omnipresent throughout the entire course on complex analysis, and you will see it again and again. In the previous segments, using a straightforward string of straightforward manipulation, appealing a little bit to the underlying geometry, the basic underlying geometry of complex numbers and their algebra, the Euler's formula, the Moivre's formula, we deduced the expression shown over here, the sum of terms that look like a complex number A. You remember the shape, keep it in your mind, see it in your mind's eye, times z raised to the power of k varies from 0 to n, is equal to the sum of these two finite trigonometric sum shown over here. And now the interesting question is, okay, what do we do? Why did we go through all these motions? Where is the tactical win? And what does it even mean? Well, before we answer that question, here is a basic fact from in general in complex analysis, but this is really nothing more than upper middle school, lower high school material or a fact about complex numbers. Let's say we have one complex number that is represented algebraically as a sum of its real part and its imaginary part over here. Let's name that complex number P. Let's make name another complex number Q, which again in its algebraic form represented as a real part plus its imaginary part. So here is the basic fact. These two complex numbers, as shown over here on the left side of your screen, are equal one another. P equals Q and Q equals P, if and only if, in parallel and at the same time, the real parts of these two complex numbers equal one another. In other words, P sub x is equal Q sub x, and Q sub x equals to P sub x. And again, in parallel and at the same time, the corresponding imaginary parts equal each other. In other words, P sub y equals Q sub y. Technically, we should write with I on both sides, but I cancels out. I is never zero, and there we go. Here we have it. That means that if two complex numbers P and Q are somehow through external reasoning, we find out, these two complex numbers must be one and the same, then these two equalities hold, the real parts, and separately but at the same time the imaginary parts must be equal one another, as captured over here on the right side. And conversely, if through tactical maneuvering or some theoretical reasoning we come with a construct which beyond any reasonable doubt leads us to utter the words between two complex numbers, their real parts equal one another. Px is equal to qx, qx is equal to px. And at the same time, separately and in parallel, their imaginary parts equal one another. Py equals qy, qy equals py. Then, in the other direction, these two numbers over here are equal. P equals q, q equals p. And again, think on your own. This is a tiny micro or nano quiz. What does it mean to us over here? What will be the next maneuver if you were to solve this problem on your own? The expression that we have developed in the previous segments is an equality, is evident by the equal sign over here, and as such, that expression can be treated as the equality of two complex numbers. One such complex number is represented by the material that sits on the right-hand side of the equal sign, and the other such complex number is represented by the material that sits on the left-hand side of the equal sign. Within the material that represents the complex number on the right-hand side of the equal sign, we have the real component that happens to match the sought-after finite sum of trigonometric functions of cosine perfectly, and the imaginary part of that material happens to match the finite trigonometric sum of the trigonometric functions of sine perfectly. And the computational objective for us is to find the alternative expressions for these two finite trigonometric sums. But why, oh why do we have a complex number that sits on that is represented by the material that sits on the left-hand side of the equal sign? Well, technically, and this is a little bit of a highbrow mathematics, the set of complex numbers, usually denoted with the fancy letter C, is the so-called complete field. Completeness in mathematics when it comes to numbers is a fairly deep property, and it's very meaningful. It takes a little bit of effort to chew through it and completely understand what it is, but by the looks of it, we're not going to need it. We will need the fact here. We will need the fact that the set of complex numbers together with four popular operations, addition, subtraction, multiplication, and division, forms the algebraic structure known as a field. So in other words, a field is an algebraic structure, which is a set combined with four popular operations, addition, subtraction, multiplication, and division, even though in grown-up mathematics, what mathematicians like to do is they like to define, for example, only addition and only multiplication, and then subtraction and division come as inverse operations of addition and multiplication correspondingly. And over the set of complex numbers, all four operations are well defined. Addition, subtraction, multiplication is defined for all complex numbers, and division is defined only for non-zero complex numbers. And what that means is that the sum, the difference, and the product of any two complex numbers is yet again a complex number, and a ratio, or the result of dividing one or any complex number by a non-zero complex number, is also a complex number. And let's take a look at the material that we have on the left-hand side of the equal sign. What do we have over here? Geometrically, we already understand we have a wild vector sum of vector units that somehow spin around or fan out in the complex plane. They all have their origin at the origin of the corresponding complex coordinate system. Their terminal points somehow are distributed over the periphery of the origin center unit circle. But algebraically, what do we have? We have products, evidently something times something. We definitely have the sum. And in general, thinking of a complex number raised to another complex number as a consequent multiplication is a bad idea. This is not the case. This is a bad idea. Do not really think that way. But especially, and even with real numbers, if we raise a real number to another real number, also thinking about this construct as a consecutive multiplication, for example, r times so on times r row times, for example, this is a bad idea. What if we want to raise number e to the number pi? How does that work out with the consecutive multiplication? It doesn't work. So, but when we have a highly specialized case, when we raise a number, be it a real or a complex number, to an integral power over here, then yes, this is a very narrow exception. We can turn this into consecutive multiplication. As such, we have exactly over here a product of any two complex numbers is yet another complex number, and a sum of any two complex numbers is yet another complex number. So here we have a complex number, and that means that that complex number can be, regardless of the underlying complexity of the computation, zigs and zags, twists and turns that sit inside this material doesn't matter. In general, that number, because the set of complex numbers is a field, is a complete field, can be represented as follows. It will be a real component. Let's designate it with fn. In general, it will be some function of a n theta plus I times g n as of a n theta. You see, this is the basic idea that you will see in complex analysis all over the place. For example, Euler used that fact more than 200 years ago to basically sum certain trigonometric series using the machinery of what we now refer to as Fourier analysis. And we will look at the mechanics of this summation at some point also. But here it is important to realize the bottom line is that on the left-hand side of this equal sign, we have a complex number that eventually can be represented that way. We don't care about the zigs and zags and twists in terms of the underlying journey, whatever it is. This is how it will be eventually represented. And because of the equal sign, we know that this thing is equal to our sum of cosines plus I times the sum of sines. I don't have much room over here, but you guys understand what's going on. K from 0 to n, k from 0 to n. And remember the previous segment, when two complex numbers, p and q, equal one another, then what does that mean? That means that simultaneously or at the same time and in parallel, the real parts must be equal one another. And what is the real part over here? Well, the real part over here is this guy. This is the real part. So this will match this. And what is the imaginary part? Well, let me use some other color. I don't know, orange, wild orange. And this is this. You see, this is this. So I'll put arrows in both directions. So these parts must match. If you're new to this, then think about it, digest it in your mind. The next time you take a shower, you stand in the grocery store checkout line or waiting for a bus, think about it, reconcile it in your mind. This is a tactical maneuver that will come very helpful time and time again in your complex analysis journey. And this is, in some sense, an infinite, in a way, source of all sorts of tactically computational convenience afforded by complex numbers. You will see the manifestation of this time and time again, over and over. And what do we do now? Well, we can say that in this case, our function, the real part of our expression, fn, will be basically a function, if you will, of three parameters, n, a, and theta, will be equal precisely to the sum of cosines of a plus k theta. You see? And k varies from 0 to n. And what is the function g of n? It will be a theta equal to the sum that runs over the dummy summation variable k that varies from 0 to n. Sum of sines of a plus k theta. You see, all this is so far is I'm explaining it slowly and thoroughly, but once you understand it, you will zip through it in less than a second. You already will know what's going on. You will jump into the technical essence and local matter that you're dealing with. You will zip through it right away. But here it is important to realize that we went through all this commotion for what? Well, the tactical advantage that we gained by going through this is exactly written here on the board. It is a difficult to solve problem to find an alternative expression for this finite sum. And it is a difficult to solve problem to find an alternative expression for this here finite trigonometric sum of sines. But it is a trivial problem over here to find the sum of what essentially geometric progression. And what does that mean? That means that all the intellectual computational burden of finding the alternative expressions for our two sums has been shifted from here into the burden of evaluating this here finite geometric sum or finite geometric series, and then unfolding that number into this here form, real part plus imaginary part. And then once we obtain these two parts, the real part and the imaginary part, through these two equations over here, bam, automatically, as if by magic, we have our alternative expression for the finite sum of cosines, and we have an alternative expression shown over here for the finite sum of sines. So what do we have to do now? Well, now all we have to do is write down the result. At this point, you will see that those of our viewers who studied the problem-solving approaches with us in a dedicated manner across seasons 1 and 2 will instantly recognize here what? Of course, reduce and conquer. Here we reduced a difficult to solve problem to a previously solved problem, because at this point in our journey, I will not be proving it. If you guys want me to, I will put together an episode that will show you the deduction for the sum of the finite geometric series. But here we take it as a previously solved problem. Here the tactical burden of doing the evaluation of the sum is removed. It's gone. We already know what that is. A is a constant real number. We factor it out. In a way, it's A times, and then what follows next is a finite geometric series, and we know how to sum that series. And we know how to sum finite geometric series. That is, on the left-hand side of our equal sign, we will have the following string of equalities. We have A times Z raised to the power of K, where the summation variable K varies from 1 to n. This is a constant number, so whether the sum is finite or infinite in a sense doesn't really matter. We write it as A times sum Z to the power of K, where K varies between 0 and n, and this is what? This is A times Z to the power n plus 1 minus 1 over Z minus 1. You see, this is it. Essentially, the game is over right then and there. This is a trivial task. This is where we win. Instead of fighting the fight with the specific finite trigonometric sums, we offload, if you will, or we shift the computational pressure, or we shift the intellectual challenge from fighting the difficult fight to virtually fighting no fight. This is all mundane. Finite geometric series, sum, and now what do we have to do? Well, precisely because, remember, in general, the set of complex numbers under the four popular operations, addition, subtraction, multiplication, and division, forms a field. It means that no matter how complex this animal may look like, no matter what the zigs and zags and twists and turns we take, usually these are quite mundane, it will be reducible and representable in the shape that is the real part plus imaginary part. You see, this is all there is to it. And then what is F? Sought after sum of cosines. And what of G? Sought after the sum of sines. That's it. And this idea will serve you well time and again. Make sure you grasp it, and that is why I spend so much time on it, because this theoretical material in some sense is where the gold is. This is very important and very useful information to understand. Once you understand this information, all the other mundane applications of that theoretical idea should be very straightforward, and you guys should be teaching me how to step tactically here and there. But so now we'll just take this expression over here, we'll unfold it into this shape, and this is a mundane task. There is almost zero intellectual voltage. And here I have to say this, guys, listen carefully. Even though the task is mundane, and many students will eventually fight this fight, and they will do the right thing, they will obtain the right results, but they will not do it efficiently. And here is my improvisation again. It is a tiny improvisation, but it shows that the pressure to be creative, inventive, and show your improvisational skills in mathematics, physics, and computer science is always on. We always look for a clever tactical maneuver. We always look for a computational shortcut through applying a little bit of intellectual effort. And here, when we, in the process of unfolding this ratio into this form, I suggest that we do the following. So now we move this expression on the top of the board just to make room. And here, as counterintuitive as it may seem at first blush, bear with me, we introduce yet another complex number, which you guys can name anything you want. I will name it epsilon, and that will be z raised to the power 1/2. Again, it may seem counterintuitive. Why? But bear with me, you will see the results. So in the, if you will, in the exponential form, this will be I theta over 2, e raised to the power of I times theta over 2, and it's in its trigonometric form, this will be cosine of theta over 2 plus I times sine of theta over 2. That much should be evident. Remember this expression over here, guys. Take a snapshot, mental snapshot. Keep it in your mind's eye for the context, for the duration, or for the remainder of this episode. I do not have much room. I will be erasing it often, but I will come back to this expression. Take a mental note of this. This is our definition. And what does that mean? Well, that simply means that z will be what? Epsilon squared. So far, so good. Now we grab this epsilon squared, and instead of z, we slug it in uniformly into our formula. What do we have? We have a times epsilon raised to the power 2n plus 1 minus 1 divided by epsilon squared minus 1. Why did Roman over here pull this stunt over here? This is another nano quiz. Think on your own, put this video on pause, walk away, compare your idea to mine. Let us now first decipher the numerator of the given complex number shown on the upper right hand side of your screen using this here cheat sheet that I wrote in a different color. Epsilon is basically a synonym for z raised to the power 1/2. You remember that expression in the exponential and in the trigonometric form. But for the numerator over here, what do we have? We have epsilon raised to the power 2n plus 1 minus 1. What do we do here? We factor out one copy of epsilon raised to the power n plus 1 times. We have another copy left inside minus the reciprocal image of that number, epsilon n plus 1. This will be what? Epsilon raised to the power of n plus 1 times what? Well, here's a nifty device. Doesn't really matter what these powers look like. It's not really as scary. Fundamentally, we have a non-zero number and it's reciprocal. So in the trigonometric form, for example, what do we have for the number, let's say, epsilon raised to the power n plus 1? This is z raised to the power n plus 1 over 2. And in the corresponding trigonometric form, this will be n plus 1 over 2 theta plus I times sine of n plus 1 over 2 theta. This is again straightforward baby arithmetic. We already understand what is going on. And what do we have for the reciprocal of this non-zero complex number? For the reciprocal of this here non-zero complex number, we have epsilon raised to the power minus n plus 1. This is z raised to the power minus n plus 1 over 2. So far, so good. And in the trigonometric form, what is it? Well, it's the same cosine n plus 1 over 2 theta. N is the same sign, but taken with the negative sign, with the minus. See, I times sine n plus 1 over 2 times theta. So this is a nifty tactical device. Whenever we have a non-zero complex number and its reciprocal, if we add a non-zero complex number to its reciprocal, then what we will achieve by doing so? Well, we will erase the imaginary parts of these two numbers and we will double the real part. And conversely, if from a non-zero complex number we subtract its reciprocal, as we have over here, what we will do? We will effectively erase the real parts, but we will double the imaginary part. So far, so good? So far, so good. So here we will have times 2 times I times the value of the trigonometric function of sine evaluated at the argument n over 2 theta. You see, this is straightforward manipulation, all courtesy of this counterintuitive at first blush substitution for epsilon, and now we carry out exactly the same computation for the denominator of our fraction. If we have any viewers in our audience who are approaching their time for entering college, they can use this material over here as a sort of preparation for verbal examination, because in my time, for example, all examinations without exceptions in mathematics, theoretical physics, and computer science were conducted in a verbal format. You walk into the audience, you pull out a piece of paper or a ticket with a number of tasks, you tell the professor the number on the ticket, the professor will write down your last name, the ticket number. You go sit down in the auditorium in the lecture hall, for example, for 15, 20, 30 minutes to compose yourself, gather your thoughts, and then you step up to the plate, and in the real time, face-to-face format, in a way you spar with the professor and you tell your story. So here you will probably not have that much time to think about this thing. So let's write down the result for this guy right away for the denominator. For the epsilon squared minus 1, we will represent it again as what? We factor out one copy, and then we will have epsilon minus 1 over epsilon. And here, let us be brave. Let us ink this result right away without any intermediate computations. We can see them in our mind's eye. We see what epsilon is. We know what z, the complex number z is, 1/2 theta exponential form, trigonometric form, plus, minus, reciprocal, yada yada. All these things instantly come out to what? Epsilon times 2 times I times the sine of what? Theta over 2. Of course, that is all there is to it. Remember, from the previously explained mechanics of the difference between a non-zero complex number and its reciprocal, by constructing this difference, we erase the real parts, but we double what? We double the imaginary parts, and voila, there we have it. So what do we do now? Well, we divide one by the other. Remember, we have the ratio. Divide, 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 and what do we have now? Cancel, cancel, choose, cancel, cancel for the i's. One copy of epsilon, one copy of epsilon. So what do we have now? Epsilon raised to the power of n times real number, real number. So this ratio over here, in some sense, don't care what it is, it's a real number, call it rho. So what do we have now? Now we have epsilon raised to the power of n times a real number, rho, and that real number is what? Well, rho times, we now unfold our epsilon using this here definition into, let me grab a new chalk. We unfold it into its, if you want in your mind's eye, you envision the exponential form, then you flip it into trigonometric form, or if you're fluent with doing this transformation in your mind's eye on the fly without intermediate steps, you write down the following. This will be cosine, just in case if you want to, n theta over 2 plus I times sine of n theta over 2. But you do not really have to do that, because remember, to this guy here, to the product shown over here, we have to add what? We have to add our favorite complex number a. So in some sense, I wrote down this expression for you because, again, you can experiment with fighting the fight with middle school trigonometric identities. Multiply this parenthesis with the trigonometric representation of our complex number a. but I will not do that. I will take a computational shortcut and we will write down the result using what? Using the wonderful arithmetic of exponents. So we will have our sum is equal to a times some real number times epsilon raised to the power of n, and that will be what? Some real number, don't care what it is the ratio, we know what it is, and then times e raised to the power ia, this is our constant real number, and then times what? E raised to the power, which one? I n theta over 2. You see, I n theta over 2. Why is that? Well, epsilon raised to the nth power is z raised to the power of n over 2. And in its exponential form, it will be what? E raised to the power of I times theta times n over 2. And this is exactly what we have. Now we collapse these two exponents into one. This will be rho times e to the power of I a plus n theta over 2. You see how smoothly these things follow. This is almost effortless, almost zero intellectual voltage, just rolling with the flow. And then there we go. We flip this exponential representation of the result into its trigonometric form. We have our rho times cosine of a plus n theta over 2 plus I times rho times what? Sine of a plus n theta over 2. You should be able to recognize this. This is straightforward. Again, baby arithmetic, nothing complicated. And we remember the definition of rho. Sine of this horrible thing divided by sine of less horrible thing, theta over 2. Game over. And what is this? Well, this, remember, our theoretical part. This is f. And what is this? And this is g. So now let us erase all these intermediate computations and write down this result in a neat and intelligible form. And if we carefully write down the results that we saw a few seconds ago at the bottom of the board, then we will have the following. Our finite sum of a basically finite geometric series over here, modulo this multiplicative constant a, constant real number, comes out to be representable as the cosine of a plus n theta over 2 times this real number, the ratio of sine of n plus 1 over 2 theta, divided by sine of theta over 2. Remember that this ratio over here we named as rho. It was a real number, and this here term represents f, plus I times sine of a plus n theta over 2 times exactly the same ratio, sine of n plus 1 over 2 theta divided by sine of theta over 2. And this part over here attached to I represents our function g, and basically fundamentally we are done, because this complex number shown on the left hand side of your screen and on the left hand side of the equal sign is representable as f plus ig. Basically all we do now, remember, we go back to a couple segments prior and we now equate f to the finite sum of cosines, and we equate g to the finite sum of sines, and we are done. Being diligent students of mathematics, we carefully write down our results for the finite sum of cosines, shown over here in blue, and for our finite sum of the trigonometric functions of sine, shown in red below. I hope I did not make any mistakes. If I did, I apologize. I usually try to carefully write these things down and make sure they are correct, because fixing and correcting these things is next to impossible in this format. But anyway, the point is that we obtained these results using a completely different machinery, completely different approach, but these results are in a perfect agreement with exactly the same results that we obtained in the previous episodes, using nothing more than the machinery of trigonometric identities at the middle school level. But in a reasonably clever maneuver, we managed to take our sums and morph them into sums that turned out to be telescopic. And now, I think I mentioned that in the previous episode, I will mention it one more time. These identities, or these formulas, if you will, can be taken further. And once you understand, for example, how telescopic sums work and how the complex numbers work and what is the connection between an exponential and a trigonometric form of a complex number whose modulus is 1, you can try your hand at evaluating the following sums. As a voluntary baby mathematical research of sort, I suggest that some of our viewers, or hopefully all of our viewers of our channel, try their hand at using, for example, the notion of telescopicity of a sum that you learned in the previous episode. Try your hand at evaluating the sums shown over here. For example, we throw out the constant real number a, and let's say the argument of the cosine is an even multiple of the argument theta, and here it is an odd multiple of the of another real number theta, and the same idea applies to the sum of sines whose arguments are even multiple of the real number theta, and here the arguments are the odd multiple, and the boundaries of summation shown over here, here, and here. And again, one reason why you want to study these sums is because they will definitely help you down the line with the theory of integration when you will be doing integrals, for example, definite Riemann integrals. The alternative expressions for the sums, you will unwind them the other way, because integrating the sums is much easier than integrating the corresponding products. And lastly, coming back to our complex, here was my humorous take at the complex numbers. If the one deduction that I showed you is just one way, again, we can improvise, and I suggest that that's what you do. You improvise. Here is another approach. I will not be doing it. This is just, again, another opportunity for you guys to do baby research on your own, the voluntary work. Go back again to the same Swiss-born mathematician Leonard Euler. Use his expression for the trigonometric function of cosine, which is a linear combination of two exponents, this one and this one. This is how it is represented. And now when you begin summing this thing, let's say from 0 to n, what will you be doing over here? Well, here you will be doing the same thing. You will be summing this here thing over k that varies between 0 and n. This is another improvisation on the theme. Why not? This sum is finite. You split it into two sums. This will be, again, this is a constant real number. There is no variance over here. So you will be essentially, again, summing. You will be summing a finite geometric series. By this time, it will be expressed explicitly in terms of an exponent, and then see where that takes you. Share your results, share your finds with us. Meanwhile, this is it for this episode. This is it for the mathematical problem S3M3. Thank you for your time. Thank you for watching. I will see you in the next episode. It will be season 3, episode 5. It will be titled Euclid Says, because in that episode precisely we will deduce the relevant formulas using the so-called synthetic planar Euclidean geometry.